yesterday. Okay. Now, yesterday I told everyone here I am going to introduce something about using the Coulomb's law. Here I'm going to give an example on that. Now, here is an example. Let's have a look on this question. Example, we have an electric field, and we are trying to figure out electric field due to a charged rod. Here we have a rod. The length is L, so a rod of length L has a uniform positive charge per unit length, lambda. And a total charge is Q. Calculate the electric field at a point P that is located along the long axis of the rod and a distance A from one end. Okay, this is a typical problem that in electric and magnetics, that usually we have this kind of problem. If we want to solve this kind of problem, what should we do? Okay. Let me repeat the question again. Okay. Let me repeat the question again. A rod of length Raman read the textbook and he told me that, well, at least you read the textbook, but it is very difficult to understand. So difficult to understand. It is difficult to understand. Okay. Now let me give you a simple question. Then charged ring. Let's start with electric field due to a charged rod. Okay? Here. Let's do something like that. Now, let me repeat the question. Okay? A rod of length L has a uniform positive charge per unit length, lambda. So this lambda is like I said yesterday, we have a volume charge density, we have a surface charge density, we have a linear charge density. Then this lambda is actually linear charge density. Basically, it's say coulombs. So how many charges? How much charges per unit length? How much charges per unit length? Okay, so that's what this lambda is. Now, has a uniform positive charge per unit length lambda, and a total charge of Q. Okay, the total charge of Q. So let me ask you a question. After we read the first sentence, I will ask you a question. What is the relationship between lambda and Q? Let's answer this question first. What's the relationship between the lambda and the Q? A rod of length L has a uniform positive charge per unit length lambda and a total charge Q. Yeah, send me the text answer. Let me make sure everybody understands the question. Send me the answer through text. Send me the answer through text. Yeah, go ahead. How about let's start from Ramen. Ramen FMD. Barossa. Okay? So, a rod of length L has a uniform positive charge per unit length lambda and a total charge of Q. Yes, hello. Yeah, just give me the answer. What's the relationship? Ramen. Yeah, send me some of the answers. So lambda is linear charge and the Q is total. Yeah, but what's the relationship? What's the mathematic? What's the mathematic relation? I need an equation. You have to put Q and lambda in the equation. So what's the equation? Relationship. What's the relationship between the lambda and the Q? Good. Very good. Very good. Okay, very good. Now, let me repeat this again. A rod of length L has a uniform positive charge per unit length lambda and a total charge of Q. Then calculate the electric field at a point P that is located along the long axis of the rod and a distance A from one end. So we are going to calculate the electric field at point P. Okay? So have you everyone understand what is the question? Yeah, I want to make sure everybody understands what this question is asking for. Okay. Well, I'm sure you don't know how to solve this problem, but I want you to understand the problems first. I really want you to understand the problem first. Okay? So, let me repeat this problem again. A rod of length L has a uniform positive charge per unit length lambda and a total charge Q. Calculate electric field at point P that is located along the long axis of the rod and a distance A from one end. Now, for this kind of problem, how are we going to solve it? Let me go back a little bit about my lecture yesterday. Basically, we are going to do an integration. That's what we're going to do. The idea is we have to divide the charge distribution into small elements. Calculate the electric field due to one of these elements at the point P. Then evaluate the total field by summing the contribution of all the charge elements, the Q1, Q2, Q3. Now, we are going to do it. Look at here. Let me, for solving a problem like this, we have to establish a coordinate first. A coordinate is really important. Like here, I will make the point P here is origin of the coordinate. Then I will draw an x-axis. So this direction x-axis. Then this direction is y-axis. Okay, so I establish a 2D 2D xy coordinate system. Now, randomly pick a small portion of this rod. Randomly pick a small portion of this rod. Okay? Now, what I'm going to do, I'm going to pick this portion has a distance from the origin is x. Okay? I assume because I randomly pick a portion of rod. So the distance I made is x. Now, because I picked this portion, this is a portion. So this is not a point. So there must be certain length for this portion. Because my x-coordinate for this portion is x. So the variation of this coordinate is the length of my portion, my small portion. So the distance is x from the origin. So the length of this portion is dx. Now, according to my first question, okay, according to the problem, a rod of length L has a uniform positive charge per unit length lambda and a total charge of Q. Then how many charges contained in this portion dx? So how many charges in the portion of dx? Yeah, send me the answer through the text. Anybody, you can do that. Send me how many charges in the portion of dx. Well, I hope, Raman, you can continue, follow my lecture. Okay? Well, of course, anybody can answer this question. Okay? So how much charges, how many charges in this portion of dx? Yeah, send me the answer for that. Okay? Raman? Anybody? Raman? Abgel? Amar? Anyone, if you like to answer my question. Lambda divided by dA. No. Rethink again. So what's the lambda? Lambda divided by dq. No. See, look at here. Like the unit length has the charge of lambda. So here, the length of dx, how many charges? How many charges for unit length. How many charges for unit length? Yeah, answer me this question first. How many charges for unit length? Yeah, Raman, answer this one first. How many charges for unit length? 3? No. It has to be lambda. The answer is the answer is lambda. Right? What's 2? Dixon says 2. Amos says 3. I don't know. Well, there's no 2 or 3 in this question. So let me ask this question again. How many charges in the portion of dx? Yeah. Send me some answer. How many charges in the portion of dx? Raman, I hope you can send me the answer. Hello? Hello? So anybody? Anybody? So you read the question. A rod of length L has a uniform positive charge per unit length lambda and a total charge Q. Okay? So infinite charges? No. So Raman? So how many? Yeah, please answer this question. So how many charges in the portion of dx? Hello? Hello? Well, no. Lambda. What is lambda? What is lambda? Lambda is the charge in a unit length. So how many charges in the portion of dx? Yeah, send me the answer. Yeah, send me some answer for that. Okay? Hello? 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 Yeah, I kept asking how many charges in the portion of dx. Send me some answer for that. Well, okay. So, if lambda is the charges in a unit length, then the charges in the portion of dx is lambda times dx. So is that correct? If the lambda is the charge for unit length, then for the portion of dx, we have the charge of lambda times dx. So is that clear? Yeah, send me some answer. Is that clear? Hello? So anybody? Good. Okay. All right. Now. Yeah. Well, cool. So you realize it's in the picture, but the picture that didn't say this dq is the amount of charge. The dq is the amount of charge in this portion of dx. Okay? Now, since this portion is so small, okay, since dx is small, so dq is point charge. dq can be seen as a point charge. Okay? dq can be seen as a point charge. So this is dq. The color with the red is dq. Okay? So for a charge of dq, for a point charge, what I meant is a positive charge. Here, for a point charge. So for a point charge, what kind of electric field we will have for a point charge? For a point charge, the electric field is Ke times Q times R squared. Okay? That's the magnitude of the electric field for a point charge. Okay? So, since the point charge is so small, so this point charge will have a very small electric field at point P, which is dE equals to K. This 1 over 4 pi epsilon 0 is K, times dQ divided by R squared. The R for this dQ to point P is X. Now let me come back here, original. Remember that between the source and test charge can be expressed like this, then the electric field I should rewrite this. So the electric field for a point charge of Q will be like this, okay? So then the electric field for point charge of Q will be like this. So this is the vector, but for magnitude of this electric field will be Ke times Q divided by R squared. Like we said before, what's Ke? We talked about Ke before. So Ke is 1 divided by 4 pi epsilon 0. Okay. Well, if you write Ke, it's okay. If you write 1 divided by 4 pi epsilon 0, it's okay. So now we have, let me come back here. So for the portion of dx, we have the amount of charge of dq. dq is a point charge. So for the point charge of dq, it will have an electric field with this magnitude, dE, which is Ke, this is Ke, times dq, divided by R squared, which is the length from this dq to point P. So divided by x squared. Now, like we said, what's dq? dq equals to lambda times dx. Okay, so which direction the electric field will have for this point charge? What direction is on the axis to the negative side? Then, like we said in previous presentation, how are we going to do that? We now figured out one portion of the charge distribution caused a small amount of electric field. So we divided the charge distribution into small elements. We calculate the electric field due to one of these elements. What we did is we calculate the electric field due to one of these elements at point P. That's what we did. Now, the third step is we are going to evaluate the total field by summing the contributions of all the charge elements. So let me have a quick question. This portion has electric field this much. And what about another portion? For example, if I pick another portion here, well, because the portion here I picked randomly, so the distance from point P is x, the length is dx. If I pick another one, the expression will be exactly the same as this one. So for another one, for another portion, for example, for this portion here, okay, we will have exact the same expression. For this one, we have another dE here, right? And for each one of these portions, we'll have the same expression like this. And they all have same direction. to the negative x-axis. So what we need to do is we add all these dE together. We add all these dE together. That will give us the total field. Okay? And that will give us a summing the contribution of all charge elements. So what we need to do is we need to do an integration on this dE. Since this one is related to x, so different portion has only one thing is different. For example, the red and the blue, what's the difference? The only difference is the distance to P, okay? So for the first portion, we have the distance is A. The most further portion, we have distance, which is A plus L. A plus L. So what we need to do is we do an integration on x from A to A plus L. That's what we need to do. And then, so for a constant, which is not related to integration, we can get out of the integrals. We can get this lambda divided by 4 pi epsilon out. And we got dx divided by x squared, integration from A to L plus A. So for this integration, I hope you've learned in advanced mathematics. If you do integration for this one, you will get 1 over A minus 1 over L plus A. Okay. So if we write this lambda equals to Q divided by L, then we will get the solution like this. Okay. Now, my turn. Do you have any question about this example? Well, I hope you can get something out from this example. If you don't, then, well, that will be difficult to continue. Now, do you have any question about this example? Yes? Hello? 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 You still there? Anyone? Are you still there? Hello? Last yellow part is for red portion. I'm sorry, what's... I don't... ramen. I do not understand your question. Would you mind asking again? So would you mind to ask it again? Okay. Okay. So, okay. Now, we can discuss this result. We can discuss or finalize this result. What if the L approaches to 0? What if the L is very small? Well, if the L is very small, then the result will be Q divided by A squared times 1 over 4 pi epsilon. So that will come back to the original result, which is KE. This is 1 divided by, so this KE, I hope you can remember this KE, okay? Let me write here. So the KE, like I said, equals to 1 divided by 4 pi epsilon 0. So this is KE. All right. Now, let me come to more complicated. Let me repeat this problem-solving strategy again. Okay, this problem-solving strategy. First one is conceptualize, establish a mental representation of the problem. Then image the electric field produced by the charges or charge distribution. Then we categorize the problem, like the problem is individual charge, or is a group of individual charge, or it's the continuous distribution of charges. Like the problem previously, we categorized this one. So what kind of problem is this? This one apparently is the one for continuous distribution of charge. Okay. All right. So this apparently is a problem for continuous distribution of charges. Then we analyze the problem, analyzing a group of individual charge or analyzing a continuous charge distribution. Like because we are in this category, so the vector sums for evaluating the total electric field at some point must be replaced with the vector integrals. Then we divide the charge distribution into infinitesimal pieces. Then we calculate the vector sum. Now, let me ask you a very quick question. Why I didn't write, a very quick question. Why I did not write the electric field in vector form here. In vector form. So anyone can answer that question very quick. So you didn't see anything like a vector. You didn't see anything like a arrow anywhere. Why? So can you give me some answer for that? Hello? This is really important. So can anybody answer? Send me some text message. Yeah. Can anyone give an answer? Can anyone give an answer for that? Hello? No? All right, let me answer this for you, okay? Simply because every portion, the electric field made by every portion here has the same direction. So when you sum vectors with the same direction, you just add them together. You just add the magnitudes together, okay? So that's why we didn't write this one as a form of vector. Now, after we got the result, we can finalize, we can check to see if the electric field expression is consistent with your mental representation. And we also check to see if the solution reflects any symmetry present. And we can image varying parameters to see if the mathematical results changes in a reasonable way. Now, I have a more complicated example going to ask you about here. I'm going to talk about electric field due to a charged ring. Okay, due to a charged ring. And for this ring, we have a total amount of charge of Q. The radius is R. And we would like to know a point along its axis, the axis of this ring. Okay, along this axis. We would like to know the electric field at point P, which has distance x from origin. How are we going to solve this problem? Raman told me that he read the textbook. I don't know if anybody else read the textbook. Okay. Well, since the time is over, let's have a 10 minutes break. Let's have 10 minutes break. And then after that, I'm going to explain the electric field due to a charged ring. Okay? See you in 10 minutes. See you in 10 minutes. Okay? All right? See you. And during the break, please try to understand this problem, this example. I hope you can understand this example. Otherwise, it will be very difficult for us to continue. All right?